here is Lenz's law, but before we go through Lenz's law, I want to remind us of one thing that we talked about earlier, last lecture, and that is how currents create magnetic fields. Let's imagine we have a long straight wire with a current going upwards. Remember, that creates a magnetic field in the direction that we find by pointing our thumb in the direction of the current, and our fingers would wrap around the wire. So let's imagine here's our straight wire, the current is going up, our fingers wrap around the wire in the direction of the magnetic field, which means over here it would point out of the board, and over on this side it would point into the board. So the magnetic field created by the current is out of the board on the left side, into the board on the right side if the current is upwards. Rather than a long straight wire, let's imagine we have a circular loop of current, and the current is going counterclockwise in this case. Well, over at this side, we have a current going up, and our magnetic field will point out of the board inside the loop, into the board outside the loop, kind of just like this over at this section. Over here, we have a downward current, and the magnetic field points into the board, out the loop, out of the board, inside the loop. Down here we have a magnetic field out of the board, in the loop, into the board, outside the loop, and up here, out of the board, in the loop, outside, into the board, outside the loop. So all within the loop, we have a magnetic field that points out of the board. So a counterclockwise current creates a magnetic field that points out of the board when we are looking inside the loop. Another little application of the right-hand rule: when you have a current in a loop, you can figure out the direction of the magnetic field within the loop by pointing your fingers in the direction of the current. Your thumb will then point in the direction of the magnetic field that is created inside the loop. So for a counterclockwise current, that creates a magnetic field out of the loop, this way. Again, if we had a current in the other direction, a long straight wire downward, that would create a magnetic field that pointed out of the board on the right side, into the board on the left side. Again, if we look at a loop with a wire, but in this case a clockwise current, we find the magnetic field pointing into the board, into the board, into the board, into the board, everywhere inside the loop. Again, pointing our fingers in the direction of the current, our thumb points in the direction of the magnetic field inside the loop, which in this case is into the board. The bottom line is that when you have a current in a closed loop, that creates a magnetic field within the loop. And you can find the direction of that magnetic field with the right-hand rule. On the other hand, if you know the direction of the magnetic field that's created, you can point your thumb in the direction of the magnetic field, and that tells you the direction that the current has to be. Very, very good. Now, let's take a look at Lenz's law. Lenz's law states, the induced EMF resulting from a changing magnetic flux has a polarity that leads to an induced current whose direction is such that the induced magnetic field opposes the original flux change. Wow, that sounds very complicated. Well, it's a little complicated, but let's take a look at it step by step, slowly. So, Lenz's law, the induced EMF. Okay, we know that a changing flux creates an induced EMF. So the induced EMF is the EMF around the loop that is created or induced by the changing flux. The induced EMF resulting from a changing flux, changing magnetic flux, okay, we're all set so far, has a polarity. Here is the statement where this is telling us the direction. Lenz's law tells us the direction of the EMF. Up until this point, we don't know whether a changing flux will give us an EMF which creates the current in the clockwise or counterclockwise direction. If we have our loop and we move our loop, remember, toward the magnet, is that going to create an EMF that goes this way, or is it going to create an EMF that goes this way? Lenz's law is what tells us the direction, and right here, has a polarity, so it's telling us the direction, that leads to an induced current. So the EMF around the loop creates a current in the loop. Whatever EMF we have that is created in our loop that has the changing flux, that's either moving toward the magnet is moving toward the current, whatever is changing the flux, there's going to be an EMF around the loop that creates a current. The current, the induced current, whose direction is such that the induced magnetic field, so when you have a current in a loop, that creates a magnetic field. A counterclockwise current will create a magnetic field that is out of the board. A clockwise current will create a magnetic field that is into the board. The induced magnetic field, that magnetic field that is created by the current in the loop, will be referred to as the induced magnetic field. This is different than the original magnetic field. Let's just back up for a second. Remember, we have, in our very first example, we had a magnet that is creating a magnetic field. We'll think of that as the external magnetic field, or the original magnetic field. Our loop then moves toward the magnet, or the magnet moves towards the loop, whichever. There's a changing flux through the loop created by that original magnetic field. There is an EMF induced around the loop, which creates a current around the loop. That current creates its own magnetic field. That is different than the original magnetic field. This magnetic field is what we refer to as the induced magnetic field. The induced magnetic field, here's the important part, opposes the original flux change. That's how we're going to figure out what the direction of the EMF is. We're going to work backwards. The first thing we need to do is figure out what is the original flux. What's the original flux through the loop due to the original magnetic field? Then, how is that flux changing? How is the original flux changing? Then, we need to find the induced magnetic field that will oppose that flux change. From the induced magnetic field, we'll figure out the direction of the induced current. We're going to do this idea, but work backwards. Rather than knowing the direction of the current and figuring out the magnetic field, we'll find the magnetic field and then use that to tell us the direction of the current, or magnetic field current. Once we know the direction of the induced current, that is the same as the direction of the induced EMF. So we're actually going to use Lenz's law and work backwards. We'll find first the original flux, and then the change in the original flux. We'll use that to determine what's the direction of the induced magnetic field, which opposes that. From the induced magnetic field, we will find the direction of the induced current, and from that, we'll find the direction of the EMF. Phew! Okay, it really sounds a lot worse than it is. But I will tell you that many times students have trouble applying Lenz's law. Let me just backtrack just for a second. We have two ways of thinking about what the EMF is. We can apply Faraday's law of electromagnetic induction completely all the way through mathematically, and the mathematics will tell us the direction of the EMF if you work through the whole thing. Or we can apply Lenz's law more qualitatively and figure out the direction of the EMF. However, Faraday's law will actually tell us the numerical value of the EMF, the quantitative numerical value of the EMF and its direction. Lenz's law will only tell us the direction of the EMF, but will not tell us the magnitude or the size of the EMF. Some problems will be able to use Lenz's law if we don't know all the numerical parts of the problem. We'll still be able to apply Lenz's law and figure out the direction of the EMF and the current. But if we actually want numerical values, we will have to apply Faraday's law. Let's take a look at some applications of Lenz's law, then we'll take a look at some applications of Faraday's law. To apply Lenz's law, we're going to try and answer 5 questions, and in this order. For Lenz's law, first, we'll ask ourselves, what is the direction of phi, the original flux? Then, what's the direction of the change in that flux? What's happening to it? The third one is the direction of the induced magnetic field. Then, what's the direction of the current, the induced current? And then 5, what's the direction of the EMF, the induced EMF? I've got 3 examples here. We'll work through all 5 of those questions for each example. First, let's imagine we have a magnetic field that's pointing out of the board, and we have a circular loop within that magnetic field. And let's imagine that the magnitude of the magnetic field is increasing. The magnetic field is getting stronger. Let's go through our 5 questions and try to answer each one. First, what's the direction of the original flux? Well, the flux is basically the original magnetic field. That is out of the board. I'm going to do this very, very physically. I like to use my arm and change the length of my arm, so to speak, as the flux changes. So our original flux is the direction of the original magnetic field out of the board. So I'll draw that out of the board. The original flux out of the board. What's happening to that flux? Well, the magnetic field is increasing. So what's happening to our flux? It's increasing. So our flux is pointing out of the board and getting bigger. So imagine my arm pointing out of the board, and my arm is getting longer. So it's getting more out of the board. So out of the board. What's the direction of the induced magnetic field? Now, here's that part where the negative sign comes in. The induced magnetic field opposes the original flux change. So the induced magnetic field is always opposite to the change in the flux. If the change in the flux is out of the board, the induced magnetic field is into the board. Be careful. The induced magnetic field does not always oppose the original magnetic field. It opposes the change in the flux. The change in the flux is not always the same as the direction of the original flux. We'll come back to that, but be careful. Keep that in mind. So the induced magnetic field is into the board. What's the direction of the induced current? We use the right-hand rule. Point our thumb in the direction of the induced magnetic field. Our fingers then point in the direction of the induced current. The current goes around the loop, and in this case, clockwise. So the current in this case goes clockwise. The direction of the EMF, the direction of the EMF is always the same as the direction of the current. If the current is clockwise, the EMF is clockwise. Very good. Excellent. Let's try the next one. In this case, we have a magnetic field that points into the page, again into the board, again with a circular loop. But now let's imagine our loop, the radius, is decreasing. So we have a large loop to begin with, but then our loop is getting smaller. So what happens in that case? Well, let's go through all of our questions again. Number 1, the direction of the original flux. The magnetic field is into the page, into the board. Our original flux into the board. Into the board. So our flux is this way in this case, into the board. Direction of the change in the flux. Well, what's happening? Our area is decreasing, so our flux is decreasing. So it's pointing into the board, but getting smaller. Everyone see that? The flux into the board, but getting smaller in this case. I'll just turn a little bit, so this way, and it's getting smaller. So what's the change in the flux? The change in the flux is out of the board. So in this case, because the flux is decreasing, the change is opposite the original direction of the flux. So the change in the flux out of the board. Direction of the induced EMF, the EMF, the direction of the direction of the induced magnetic field. The induced magnetic field opposes the change in the flux. So it opposes the direction out of the board, so the direction of the induced EMF is into the board. it is in the same direction as the original flux. General rule is, just keep in mind, if the flux decreases, the induced magnetic field is in the same direction as the original. I'm going to hold off on that. I'll hold off on that, and we'll come back to that in a second. Okay? All right, number 4, the direction of the induced current. Again, point your thumb in the direction of the induced magnetic field. That tells you the direction of the current, in this case, clockwise. EMF, same direction as the current. Direction of the EMF, always the same as the current, clockwise and clockwise. Very, very good. We happen to get the same direction for the current and the magnetic field, and the induced magnetic field in this case. All of those because the change in the flux was in the same direction, although our original flux were in opposite directions from these two problems. All right, let's try one more. In this case, we have a magnetic field pointing into the board. Here we have a loop, but now the loop is moving this way. Imagine that our magnetic field stops over here and our loop is moving further into the magnetic field. Kind of like our original question where we had the net, we're putting the net and the net is getting down into the water. More of it is coming below the surface. So here's our loop, and it's kind of coming through the surface, getting further into the surface like this of the water. But in this case, it's into the magnetic field. So here's our loop, and our loop is moving into the magnetic field. More of the loop is coming into the magnetic field. What is the direction of our original flux? The original flux is into the page, into the board. The direction of the change in the flux. As the loop moves in, what is happening to the flux? Is it getting bigger or smaller? Well, as the loop comes in, more area is within the magnetic field, so the flux is increasing. So it's getting more into the page. What is the direction of the induced magnetic field? The induced magnetic field opposes the change in the flux, so it is out of the board. Using the right-hand rule, current is counterclockwise. EMF, the same, counterclockwise. Well, and notice that we went from clockwise in this case to counterclockwise, and again, because we had change in the flux of out of the board to a change in the flux of into the board. Very, very good. Excellent. Let's take a look at some numerical problems where we'll actually stick some numbers in here. And in that case, we can apply Lenz's law to see if we get a direction for the EMF, but that should match the direction that we also get from Faraday's law of electromagnetic induction. Let's take a look.